Alright, so in this tutorial, we are going to move from angular kinematics, which looks at the relationship amongst angular velocity, angular displacement, and angular acceleration, to dynamics, which is basically a fancy way of saying when forces get involved and there's an acceleration. We're going to develop essentially the second law of motion again for angular accelerations. We'll see that it's very similar to what we have for linear, with an important twist in that the inertia component that we find in linear is different and more complicated for rotational. So pay close attention to this concept of moment inertia, which will come up. All right, so let's start quickly. So we have, let's say, a box right here, an object that is exerted a force on it tangent, and there's a string here, so it's going to go around in a circle. Okay, and we're going to say that force is continuously acting on it, and that's the only force. So we know if there's a net force on it, it must accelerate. Okay, and it will accelerate tangentially, meaning it'll just go faster and faster and faster, and of course it'll accelerate radially. In other words, the centripetal force will always be there because it's turning inward, and in fact that will keep going up as the speed goes up. But because it's rotating, we're also going to have an angular acceleration. Okay, whoops, alpha. Okay, we're a little fishy. So in other words, we know it's going to spin at a greater and greater and greater rate. And we want to understand how to calculate that rate based on knowing that force and how far away it's acting from the pivot point. Okay? And so what causes an angular acceleration? Well, not a force in and of itself, because where the force acts makes a big deal. If I put the force right there through the pivot point, there is going to be no angular acceleration. So we know it's got to be a combination of F and where it acts. In other words, it's nothing more than the torque. Tau. Okay? So what we want to do is come up ultimately with an equation that relates tau to alpha. And to do that, we got to start with what we're familiar with, and that's, of course, the second law of motion. Okay, and we're going to do some manipulations. Manipulations are simple, but they might not be obvious, so take your time to try to see this through. All right, so we want to ultimately relate the value of tau, okay, to the mass of the object and the angular acceleration. Okay, so to do that, we got to start, like I said, with what we know is familiar, the second law, where we have F equals ma. All right, so if we want to relate to angular acceleration, there's a simple relationship between a, which is in this case a tangential acceleration, and alpha. We learned that yesterday. That's nothing more than alpha times r. All right, we'll come back to that. If we want to express the second law in terms of torque, then the difference between F and torque, right, if you recall, torque is equal to F times r. So I would take both sides of this equation and multiply by the radius. So let's do that. So we have F times r is going to equal m times a times r. Now let's do our substitutions. F times r we know is torque. M is still going to be m. A we saw is equal to alpha times r, and we still have it multiplied by r. Okay? So if we simplify that, we have tau equals m times r squared times alpha. Now let me rewrite that. We have alpha equals tau over m r squared. And that's kind of what we're after. Now let's talk about this denominator. Normally this would be a equals f net over m. So the mr squared is kind of like our inertia, except that it's not inertia because it's not just mass. So it's the rotational analog to mass. And it is called moment of inertia. Okay, so let me repeat that. In the normal second law, A equals F over M. M is the amount of inertia in the system. In our situation right here, instead of M, we have mr squared. So that's not quite inertia, but rather called the moment of inertia, and that symbol is I. Okay? So, and what is a moment of inertia? How does it differ? Well, it depends on the mass, okay? But it's more than that. It's this distribution of mass. In other words, where is the mass located relative to our pivot point? And that, in turn, really depends on the shape of the object. And so, in a solid sphere versus a hollow sphere versus a cylinder versus a ring or a hoop, the mass is distributed differently, so each one has a different moment, even if the overall mass is the same. Okay? So it is how it's distributed relative to the axis of rotation. And we'll see what that means in a few minutes. rotation. Okay. So how do we calculate moments of inertia for different shapes? Well, the first case we look at a system of particles. If I have a bunch of spheres that are, let's say, connected together, and we have different axes of rotation, which we'll see below, so don't write that in. All right, so the general equation, we kind of just saw it up there, is by definition, I is equal to the sum of the moments of each object, and each moment is r squared. Okay, where r is the distance from the axis of rotation. So that axis, where you choose it, is very, very important, and the units would be kilogram meters squared. All right, so let's look at a very important case. This is going to come up again, so pay very close attention. So let's say I have a system of 4 spheres that are connected by very light rods, and each sphere has a mass of m. Okay? And we're going to have them rotate as a unit, all 4, they're connected, remember, about 3 axes. One axis is here, another axis is here, and then the third axis is there. So let's treat each one separately and see, because of the way they are rotating, that the moments of inertia are very different, and therefore their accelerations are going to be different for a given torque. Okay, so let's do axis 1. So what we got to do is we got to see how far away each mass is from that axis, the shortest distance. So if this length from here to here is L, as given down here, and this is L down here, then it makes sense that each sphere is L over 2 away. So we have L over 2, L over 2, there's no negatives in this case, L over 2, L over 2, so we do that 4 times. So our I, for that one, is going to equal 4 spheres, each one has a mass of m, and each one is L over 2 away, and we got to square the whole thing. Okay, you could do m L over 2 quantity squared plus m quantity L over 2 quantity squared, etc. 4 times. But I'm just combining it all. Anyway, if we simplify that, that turns out to be nothing more than m times L times ml squared. Okay. How would that compare to the next situation where we decide to rotate it about this axis right here? Okay. In one sense, these two guys are not rotating. They're not any distance away. And these guys are even further away. So how does that combine overall? Will we get the same thing as this, or will it be different? Well, that's not too bad. So let's take this guy. How far away is it? It has a mass. It's L away squared. This guy is also L away from the axis. So that's twice that. This guy, the axis passes right through it, so there's no distance away from it. And the fourth one also passes through the axis, so there's no distance away. So our total for that, we'll call I2, is 2ml squared. And 2ml squared is twice that. So that would be more difficult to rotate for a given torque, right? You wouldn't necessarily expect it. That's the odd thing about rotational. It's where the mass is and where you choose the axis. Now, in the last one, we choose our axis to be right through there. So imagine these guys going tumbling head over heels around that axis. Well, what's different in this case versus the first case is that we're further away. From here to here is L, and from here to here is also L. So it's going to be the same for all of them. So we have, again, 4 of them that are each L away. So 4 mass, each is L squared away. And that's all I have to do. So the I for the third situation is 4ml squared, which is twice this, and 4 times that. So that is the axis that would be most difficult for those 3. The question is there another axis that would be even more difficult? And the answer is yes. I'll leave it to you to try to figure out which axis of all the possibilities would be most difficult to rotate around. Okay, now, what if we have an object that is not a bunch of spheres that are connected together, but just a general shape, like a one sphere that's trying to rotate about an axis, or a cylinder is trying to rotate about an axis? All right, here we need calculus, and we're not going to do the calculus, but here, in this chart here, we see common shapes and different axes, how their moments are calculated. Notice that they all have an mr squared component to it. There's just a fraction in front of it. So you don't have to memorize any of this. This will always be given in a chart form or in a particular problem. But we want you to notice, if you take a solid sphere and you rotate it about its axis, its moment of inertia is 2/5 mr squared. Whereas if you have a hollow sphere, okay, it's 2/3. So a hollow sphere has a greater moment than a solid sphere, basically because more of the mass is concentrated far away from the axis. Whereas in a solid sphere, it's evenly distributed. So which shape has the greatest moment, which shape will be the most difficult to rotate? Well, the one with the highest moment would be the hoop, okay, again, because all the mass is concentrated far away from the axis. And which one would be the least moment? It turns out, if you look at these, is this guy right here, a rod, when you go about the center. Okay, if you try to take the same rod and rotate about its end, it's got 4 times the moment. All right, so let's bring it together here. We've been trying to come up with a second law. We've understood the relationship between force and torque and alpha and A, and then we just developed this idea of moment of inertia. So when we put together, we can say that the angular acceleration of an object is equal to the net torque divided by its moment. Okay, that's very similar to saying A is F net over M, where I depends on the mass of the object and its axis of rotation. So let's do a quick little problem, number 2, and then we will do 3 in class. So let's say I exert a force of 1.5 newtons on a pulley or a wheel that is free to spin around an axis. There is no friction. We want to know what the angular acceleration is. Okay, so we got to make sure we look at all forces. So we have this force. Let's say this is on a frictionless surface. All right, so there is mg down. Sorry, that should pass through it. And there is a normal force up. Neither of these contribute to torque because they pass through our axis of rotation. So our net tau, tau net, is going to be just a 1.5 newtons. Okay, even though there are 3 forces, there's only 1 torque. So to find the angular acceleration, we would just use our second law. It would be tau net, I'm just going to put tau here, divided by the moment. Well, this we already established is 1.5 newtons. Well, how do we find the moment? Well, that depends on the shape that we're rotating. So you're told this is a solid disk, which most pulleys are. So if we go back up to our chart here and we find a solid disk, all right, it's really a solid cylinder. We're rotating about that. We see that its moment is not mr squared, but 1/2 mr squared. So we take the mass of the pulley and we take its radius and we do 1/2 mr squared, okay, and then we can get a value. So I'm just going to, okay, whoops, my bad. My tau here is going to be 1.5 times the r. Okay, that's the radius. I made this classic mistake of just confusing it with force. So I have 1.5 newtons times r all over 1/2 mr squared. So if we do that, we get 1.5 times r over 1/2 mr squared. We see that one of the r's cancels out, the 1/2 comes up on top, and we have 3 all over m times r. If you plug in the numbers for that, okay, you will get 300 radians per second squared. Okay, so again, tau net is 1.5 newtons times r, and the moment of inertia is based on the shape was 1/2 mr squared. Okay, and then I ask what length the string will be let out after 1 second. That's now a kinematics problem. Okay, what length, all right, is L? Okay, this is T. What we found is alpha. So if we want to find L, all right, that's a distance. I'm going to say distance equals V naught T plus 1/2 AT squared. All right, where this is initially 0. But I don't have linear acceleration, but I can get that because I know linear acceleration equals angular acceleration times r. Okay, so I can subdo that calculation, put it into here, and when I work it out, you should work this out for yourself, you get a length equal to 7.5 meters. Okay, so try that for yourself. Make sure you can do that. All right, so we'll do problem 3 in class. It's very similar to this. We have the same pulley. We have the same downward force of 1.5 newtons. So we want to know what's the angular acceleration going to be. Okay, so ask yourself, is it going to be the same as this, greater than, or less than? And we'll talk about that in class.